start off this part of chemistry, we're going to be starting with a unit called the mole, which is a unit that we're going to be using in chemistry to help us count particles. And so let's kind of dig in and start off with a little bit about measuring matter. There are several different methods that we can use to measure the amount of something that we have. For instance, we might say that we have a 6-pack. We might say that we have a 24 24 in a case of pop. We might say that we have like a 5-pound bag of potatoes, so we use mass. We also use volume whenever we talk about a gallon of milk or a 2-liter of pop. And we can also convert between these measurements. For instance, when counting, we know that a dozen is equal to 12. When we do mass, we could take those dozen apples and get a mass. What is the 2.0 kilograms, for example. We can also take that counting amount and convert that to a volume by using something like bushels of apples. So we're going to start off with a conversion. We haven't done any for a little bit, so we need to practice. And I'm going to get this to a better color here. Alright, so there's some information that we have in our problem. First of all, we know that we have 90 apples, and we are trying to find the mass of those 90 apples. And so there's some information that we're going to need to be able to convert this. First of all, we need to know that 1 dozen is equal to 12 apples, because we don't know how many dozens of apples we have. We just know we have 90, so we have to convert that into dozens. And then we know that for every 1 dozen apples, we have a mass of the 2.0 kilograms. So we know that a 1 dozen is also equal to a certain amount of mass. And we're going to be using these conversions to take our 90 apples and get it to mass. So we have 90 apples. Now, of these two conversions, we need to pick which one would be the most useful right now. And the only one that has apples in it that we could put into our conversion bar here is the 12 apples. And that would need to go on the bottom so that apples will cancel. And we're going to put 1 dozen on the top because that equal sign is saying that that's kind of our division bar. So now our apples are gone and we're left with dozen. And now that we have a dozen apples, we can convert the dozen apples to a mass, 2.0 kilograms. So our dozen apples will also cancel. We are left with mass, which is the unit that they asked us to get to for mass. And significant digit wise, when we're recording our answer, we also need to know how many numbers we're allowed to record. So the 90 has 2 because that decimal place allows us to have the 2. And if you're counting a certain number of apples, then obviously if we say 90, then we have 90. We can't have, it might not be 90. If we say 90, we really have 90. So this is also an absolute, the 1 dozen over 12. We don't count this as far as significant digits. And we have the 2.0, so we have 2 decimals there. So our final answer needs to have 2, and calculator-wise, if you take 90 times 1 times 2, and then divide that by 12, you would get 15. And kilograms, again, is the unit that we had at the end. Alright, so as far as kind of moving away from bushels and kilograms and so on, chemistry is very much a quantitative science. We do a lot of counting. We have a lot of numbers with units. And back in elementary school, or maybe still occasionally, we count on our fingers. But in chemistry, we can't really do that. We're talking about atoms and protons and neutrons and electrons, all things very too small for us to even see, let alone count on our fingers how many there might be. So we're going to be using what's called a mole. Now we have the little fuzzy mole that lives underground, not the type of mole that we're talking about, although in chemistry we even have a day associated for the mole. People do mole celebrations. But a mole is a certain amount to it. So 1 mole is going to be equal to 6.02 times 10 to the 23rd representative particles, and we'll talk about representative particles here in a few minutes. Now the mole is going to be a very common measurement. You're going to see it frequently. It is the standard, the international standard for measuring the amount of something, so it is used worldwide in our metric system. And this was given to us by Amadeo Avagadro, and that is his full number here if you look at all of the decimal places. And so we round it to 6.022. We'll be using 6.02 times 10 to the 23rd in class. But he is the Italian scientist, and he clarified the difference between an atom and a molecule. So an atom, for instance, like nitrogen, whereas a molecule would be N2, where it's bonded to something. And then we have representative particles, and a representative particle is any particle that something is made up of. So for example, you have a chart here that you're going to be filling some information out on. If we're taking a look at an element, for example, elements are made up of atoms. Atoms of nitrogen or atoms of oxygen, that's the nucleus with the protons and neutrons and electrons. If we're talking about our covalent compounds, okay, those are made up of molecules. Molecules, for instance, all of these are covalent bonds. They're all nonmetals that are bonded together. Ions are just made up of ions. We could have positive ions, cations, negative ions, so all your polyatomic ions. And then we have ionic compounds, and those would be our metals and nonmetals bonded together, and those are representative particles called a formula unit. Now, we're going to be doing some conversions so that we can practice using our new Avogadro's number, 6.02 times 10 to the 23rd. And we're going to be converting how many atoms there are in a certain number of moles of propane. How many atoms are in 2.12 moles of propane. So again, we're going to start with what we know. We know that we have 2.12 moles of the C3H8. And we want to convert that. First of all, the only thing that we know of that goes with moles is our, in this case it's going to be a molecule, because C3H8 is a covalent compound. So we're going to have 1 mole of our C3H8 is equal to 6.02 times 10 to the 23rd, and our representative particle on our previous screen was molecule. But we're not done there, because we want to get to atoms. How many atoms are in 2.12 moles? So for every 1 molecule of C3H8, okay, for every 1 C3H8 you have, we need to know how many atoms make up that molecule. So we have 3 carbon atoms, 3 carbons. We have 8 hydrogen atoms, so 8 hydrogens, and 8 plus 3 gives us 11 total atoms in C3H8. Now every molecule or every ionic formula would have a different amount of atoms. You have to kind of count those up for each case. And for this one we need to multiply 2.12 times our 6.02 times 10 to the 23rd, and then we need to multiply that by 11, and we're dividing by 1, so that's not going to affect us at all. And when we are then reporting our final answer, we need to have 3 significant digits. This 11 is kind of an absolute. We don't use that one because there are exactly 11 atoms, and we're not going to be using our 6.02 times 10 to the 23rd. We kind of consider that an absolute value as well, and we are going to have just the 3 that we started with. And so when we calculate this out, you're going to find that you get a pretty large number. So I'm going to throw some of those numbers up here, and that is to the 25th at this point. And we don't need all of those. We have 3 to start with, so we're going to keep the 1, the 4, and that 0 is significant. It's between 2 non-zero numbers. So the 3 was going to be used for rounding. Do we round up? Do we keep it the same? And 3, we keep it the same. So 1.40 times 10 to the 25th, and that is how many atoms are in 1 mole, 2.12 moles of our C3H8. Now, keeping in mind that we have done a converting to atoms problem, I want you to take a look at this one. This is exactly the same problem, only we're starting with excuse me, a different number of moles and a different molecule to start off with. Excuse me again. You're going to be doing this one. I'm not going to put this one up here. You're going to be working through this one following the example I just gave you. I'm going to be checking it in your notes though, so by not doing it, you won't be getting your full participation points for doing the notes. You're going to be using the same conversions. We have to go from moles to molecules, and then we have to go from molecules to atoms. The number of atoms, though, this time is not going to be 11, so you're going to want to look at SO3 and count up how many atoms there are. And you're going to want to convert that. You're going to want to look at significant digits and all of that. So you're in charge of doing letter B. If you have questions, come see me before class, but you are in charge of that one. We're going to do this last one together before we finish up for the day, and this is how many moles are in 4.65 times 10 to the 24th molecules. So now we're kind of going backwards. We're starting with the number of molecules that are in NO2, and we want to figure out how many moles that would be equal to. So we're going to start with our 4.65 times 10 to the 24th because that's how many they tell us we have. And we have molecules, LES, molecules of NO2. Alright, now we want to get rid of molecules of NO2, so we know that for every 6.02 times 10 to the 23rd molecules, just spelled that wrong, sorry. For every 6.02 times 10 to the 23rd molecules, we have 1 mole of that. So this is definitely a conversion you will be using frequently. So for every 1 mole, 6.02 times 10 to the 23rd molecules. And for this problem, we are left with just the math because we only have a one-step problem here. We're already at moles, which is where we're at in our problem. If we divide these and take a look at significant digits, there should be 3 significant digits in your final answer. So again, to just throw some numbers up here so that you can kind of get an idea of where we're at, we want to keep 3 numbers. So the 7.72. We do look at the next number though, the 4 in this case, for rounding purposes. So the 4 isn't going to change it. So 7.72, and that is how many moles of NO2 we would have in 4.65 times 10 to the 24th molecules.